Hello, it's Duncan. I thought I was done with our package diagramming code, but then I went out for a bike ride and the blood rushed to my head. So this week, instead of writing production code, we're going to look at using ClassGraph to analyse all the code in our deployed app with the aid of improving cohesion and reducing coupling. Do I procrastinate? I'll have to ask. Oh, that's rather nice. Our recent build refactoring has been driven by this package diagram. It shows which packages depend on what. So we have things in the root that depend on things in the common Gilded Rose package. They in turn depend on things in common Gilded Rose rendering, which depends on domain. Pretty much everything depends on foundation, and so on. This diagram is generated by this package analyzer code here. And you can see here, for example, that it works by walking down from source main. It finds all the files that end with KT, and it extracts the packages and imports by looking at every line in the file, looking for the package statement and looking for import statements. Now there are two problems with this. The first is that now we have multiple modules. We have app and core and database and foundation as well as experiments. This code will only be looking in one source root. So the package analyzer is in the tests of app. So it will be looking in source main Java in our app module or Gradle subproject. So it now won't be scanning out other projects. So we could, I suppose, run it in each of the projects and then merge the information in some sort of way. But that does sound like hard work, especially as this has another problem, which is that it only actually looks for import statements. And if, for example, we would go to this main, and instead of having these imports, import common Gilded Rose app, we'd added the full qualifier to this, now we wouldn't have an import and we wouldn't see the dependency. Now it occurred to me the other day that in order to get Package Analyzer working properly, we had introduced ClassGraph. And we use that to scan our class path in order to establish the names of all the classes. Now ClassGraph doesn't care about the source, it only actually works with class files. And one of the things that I happen to know about class files is each one knows all the references to other classes that it needs. So if I return to the now reverted main.kt and ask tools Kotlin show Kotlin bytecode, here it is. And you can see here that all the types are fully qualified. So if we were to parse this class file and look at the types, we could work out all the classes that it depended on, and hence their packages. In fact, it turns out that ClassGraph can do that for us. So if in here, instead of saying enable class info, we said enable interclass dependencies, then ClassGraph would sort it all out for us. So let's see how far we can get with that technique. I'll just undo that, and we'll work in this package analyzer file, but maybe we'll start ourselves a new test main at the top of it. So we'll call this main2. And we're going to create a new class graph, and we're going to ask it to enable interclass dependencies, and then we're going to say scan. And that brings back not a class graph, but a scan result. So we'll call that scan result. Now the beauty of class graph is that it's running in the context of this process, which means that it will see the class path of the tests of our app, and the class path of the tests of our app will see the class path of the main of our app, and the class path of the main of our app will see the classes that are built in core and database and foundation and so on. So ClassGraph has access at this point to all the classes loaded by our app. Now what can we do with that scan result? Well, we can say scan result dot class dependency map. Let's have a look at the type of that. It is a map of class info, and class info is everything that ClassGraph has gleaned by parsing the class file. And class info list, which is a mappable info list of class info. I'm going to take a punt and say maybe we could just treat that as dependencies and put in the type and then say that's all very interesting, but A, we want to treat it not as mutable, so we'll take that out, and B, maybe our class info list is a list of class info. And that compiles. Brilliant. So let's just ask a question. How many classes do we have loaded? So we'll say println. Well, the completion is pretty good there. I'm just going to put another println in here because I want somewhere to put a breakpoint in order that we can use the debugger to have a look at those dependencies. So we'll run main2 in the debugger. It takes a little time. And here we can see that our dependencies has 16,862 classes in it. Now, obviously, we didn't write all of those, and in fact, we may not use most of them. They're the classes that are in all the jar files that our app is using, in fact, that our tests are using. Let's drill down into this. You see the first thing is a class from Undertow, Here we've got Augur Apache HTTP client, something from Jackson, and so on. So that looks plausible. Let's stop this. What I'm going to do now is use this dependencies to look up the first level dependency for our main. So here's our main, and we have a bit of a problem because there's not actually a class here. But if we go into where this is built, let's have a look in app build classes main. You can see in the root here we have this main kt.class. And oh, here it is. You can see it actually has our main function in it. So because in Java all code needs to live in a class, Kotlin makes up a class, in this case called main kt.class, to contain the code that's at the top level in this file. So I think we should be able to remember main kt, go back to our package analyzer and say, let's go to the scan result. So this is our root, let's say, is scan result. And the suggestion here is get class info. That's pretty close, but I want to say not com gilded rows. I want to say for main kt. And now we can get that class info and use it to look up in the dependencies. So we say val dependencies of root. Well, yes, that. Now we expect that to be a list. There it is. So now we can say dependencies of root for each println it. Yeah, that'll do it. Let's run that. Okay, there you go. And you can see from this that toString on a class info is, well, really quite binary. So instead of printing it, we'll say it dot, and the package name would be handy and the name of the class would be handy. Something like that. Let's try that. Okay then, let's have a look at the list we've got. Quite a bit longer than you might expect, but you can see that com gilded rows app is there and com gilded rows companion is there. Why is that? We click through here. Yes, in fact we're calling invoke on the companion object, so we need to pull that in. We've got roots.kt. Why is that? Oh, that's interesting. We can click through. Brilliant. That's for our roots here because our main calls roots and so on. So we are in fact seeing all the classes that we have defined that our main depends on. In addition, though, we're also seeing some other things. We're seeing Kotlin metadata. I don't know what that's for. We're seeing Kotlin pair. Well, I guess that's this 2 here. We're seeing since Kotlin, don't understand, tuples, who knows, and some Kotlin annotation things and some JVM function things. So all sorts of things the compiler is just adding for us. Plus then we're getting some pieces from HTTP, so the environment and our server. Okay, what's next? Well, it would be nice to have a graphical representation of what we're doing. And previously we had this generate dot file that took an output file name and a map of string to set a string, where the key was the package name and the set of strings was the dependency package names. So if we can get ourselves a map of string to set a string, we could use it to diagram. And at our first level, the key will be the package of our root, and the values will be the set of all the package names. So I think if we said here, we map each one of these things to it.packageName, and then say to set, then we could have package dependencies is map of root to that thing. And now we can take these 2 lines, put them into here, and that's generate the dot file. We say we want a file of new packages. Let's see what we get. Okay, it ran. Here's our new packages.png, and that looks quite promising. Okay, so far we have the packages that are dependencies of our single root class. But that obviously isn't everything. What we want to do now is go to the classes that main depends on and do the same thing. So let's sort of spitball that by making this a mutable map. And then as completion suggests, we'll go through each one of our dependencies and we'll say that we've got dependencies of the dependencies is looking up in the map. And then we'll populate our package dependencies. So we'll say package dependencies. And I've got to say the AI is doing some pretty good jobs here, although I'm not sure about that bit. So let's get rid of that. And then you can see what we're doing here is we're going down another level and we're populating the map 1 layer down. This can't live, but we'll just run it anyway. And have a look. And lo and behold, we have, well, a lot more complication, but I think if we work it out, you'll see that we only have 1 additional layer. This is obviously way too busy though, and this code can only cope with 2 levels. So let's rewrite it, and I don't really have a good refactoring for this. What we're going to do is we're going to say, if we had a private fun walk class tree that took some root, which was a class info, and took our map of dependencies, which the AI suggests is mutable, but I don't think we want to be. And also we know it is the type up on line 29 here, this thing here. So it's that, and we're going to use this to populate our mutable map of string to string. So this is, I'm going to call it destination, and the AI has correctly predicted that's mutable map of string to string. Good. Okay, put these on separate lines, go down into here. Now for each layer, we want to go and get the dependencies of that root. So this will be dependencies of root, is look up the root in the dependencies. And just in case there aren't any, I think maybe we'll say that that is an empty list. Now we want to populate our destination for this root. So we're populating our set of package names for this root with the set of package names for its dependencies. There's a problem there though, and that is that there's generally more than one class in a package, and this will overwrite. So we'll only get the last one we looked at. Luckily Kotlin has our back, and we can say destination get or put. We look up with the root package name, but if there's nothing there, we want an empty set. And having done that, we want to add all this thing. Now that's not compiling because I think we need to put brackets around all of that. Maybe not. This empty set is an immutable empty set, but we need a mutable set. And this now needs to be mutable set. So that's that line there. We can get rid of that. So that code is going to update the root, but now we need to walk down into the children. So we need to say dependencies of root for each, walk the class tree, given a new root with our dependencies lookup and the same map, so we can populate that. Let's give that a go by plugging it in here. So our package dependencies is going to be this mutable map of string to mutable set of string. And then we're going to say walk the class tree from our root, populating that package dependencies, and then we should have package dependencies populated so that we can generate a dot file from it. Worth a go, worth a go. Oh, except that we have a Stack Overflow error. In order to work out why, let's just println the root's simple name. That may give us enough clues. Here we go, and you can see we're starting at main, we're going to app, we're going to 1, and then app, and then 1, and then app. What is 1? Let's change that to name, see what we get. There we go, and we have com Gilded Rose app and com Gilded Rose app $1. Now I know from my Java days that these $1s are something to do with inner classes or something like that. Let's have a look, see whether we have any inner classes in here. We might, I suppose. Let's park that for now though, because we seem to have a circular problem here. That app is depending on app1 and that app1 is depending on app and so on. So we're just going around in circles. In order not to go around in circles, I guess we're going to have to remember which classes we visited. So let's add a parameter to this, which is visited, which is a mutable set of class info. And initially empty, that's good. And then in here we can say if visited contains our root, then let's not go down any further. Otherwise we will add our root into visited. And finally we need to pass the visited down into our recursive course. So we'll put that in there. So that should break the cycles. Let's run again. And we can see now lots and lots and lots of classes going all the way down. And if we look at our packages, then we have nothing. Now then, I'm pretty sure that's just that we've got a diagram with, goodness me, who knows how many different boxes in it. That would be loads and loads and loads. So we probably don't want to be producing a dependency diagram for not only our classes, but also the whole of the rest of the class path. I think the easiest way to do that is probably to take our dependencies of root here and filter them to find only those where it.packageName starts with com.gildedrose. Let's have a look at that. And here in the output you can see we've got a lot fewer lines, which hopefully means that our package diagram, well, it's renderable. Let's have a look at it. So starting at the root, you can see we go down to com.gildedrose, and then that uses Jackson and lots of different things in Jackson, goodness me, but also Kotlin IO and so on. Looking at this, we never seem to be finding dependencies of packages that aren't our own, but we are finding a lot of those dependencies. We solved that problem last time by filtering out some packages and eliding others. Let's go and have a look. Our previous diagram used this name for that takes a package name as a string and whether we want to include external packages. And if we want to exclude external packages, it elides COM_FASTER_XML Jackson to Jackson, org Apache HC to Apache HC, org Duke into Duke, and so on. And it also has the ability to return null, which means that we don't want it on the diagram. Might be clearer to specify the return type there. So let's see how we could use that. Back in our walk class tree here, I think let's pull out the thing we're going to mutate. That's a variable of package dependencies. And now instead of adding all the dependencies of our root with their package name, we will take name for that package name. So we don't want to include external things for now. And that's nullable, so we will map not null. And that, at the moment, I think should mean that we only get the common gilded rose packages. Let's have a look. Well, it runs. Let's have a look at the diagram. Oh, that's rather nice. I'm going to put it side by side with the other packages .png. Let's move that over there. And a bit of studying shows that these are effectively the same diagram, except that the one on the left, the new one, now includes things like common gilded rose HTTP that are in other Gradle projects. Because ClassGraph is seeing those because they're on the class path. And the same is true then for common gilded rose persistence. That is now seeing down here common gilded rose DB tables and common gilded rose DB and so on. This little package down here is all of our generated code by Duke, which in our other diagram has just disappeared because we weren't looking at the generated source. Another interesting little wrinkle here is these lines here from a box to itself. And that's showing where classes in a package refer to other classes in a package. Is there anywhere that doesn't happen? Well, it is happening down here, but I suppose we've only got one table, so that might make sense. So this is a useful diagram. It shows our nice top to bottom flow, except here in the generated code where packages do talk to each other. It would be nice though if we could see the external technologies that these packages are using. So what if we made this include external to be true? That gives us this, which is really very busy, but might be less busy if we remove things like all JetBrains annotations, Kotlin collections, and so on. And we can do that by returning null for those packages in this name for. So let's add a few of those. We'll say if it starts with Kotlin, then we will return null. If it starts with all JetBrains annotations, we'll say null. And now here we are, we're seeing some external packages. Things like org HTTP config is being used by Gilded Rose config and by our root. Duke is being used by common Gilded Rose persistence and all of our generated code. That's not surprising. The Hikari connection pool is being used by persistence. And over here we have bits of HTTP4K being used. The filtering and the lenses and the client and the routing and so on. We seem to have lost Kotlin XHTML in our rendering. And likewise coroutines for our foundation. I suppose we could put those back by saying before we ask whether it starts with Kotlin, we'll ask whether it starts with Kotlin X. And if it does, then we will let that out as the imported package. We can see now that foundation and pricing both use coroutines. I'm not quite sure why pricing does. I'll have to look at that. But also over here, rendering uses Kotlin X HTML. Oh, a bunch of different sub-packages. That's annoying. So let's say if it's Kotlin X.html, then we will return Kotlin X HTML. And that's really not a bad diagram, I think. I think in here we could say if imported package is empty, then we want to be root, else those other things, then make that into a when. That's quite pleasing. We can tidy this up a bit by changing the signature of this walk class tree. We've already had it create this set of visited things itself, and we could do the same with this destination. We could say this is a mutable map of. And then at the end, we can have the thing return that. So we say return destination, changing the type as we go. And then we have to return the destination in here. And I think we might as well say else in there. Oh, of course, we need to return it. Now then, callers of this don't have to create the package dependencies. They can just fetch it from walk class tree like that, and we could get rid of this name. If we had reordered these in here. So we'll order them to say that our external interface, if you like, is that we pass in a root and the dependencies and whether or not we want to include external ones. And then the mutable state is managed by the function itself. So if we make that refactor, there we go. And now we can say remove that argument. And I think maybe tighten that up like that. Remove that printman from there. Take this thing, I think, and make it root package name. And I think it might be clearer if this thing was some variable, which we'll come back to if we inlined that one. Dependencies of root is a bit weird. Maybe we could call this class dependencies. And I think the pipelines always look a bit nicer when we see them that way. Now that we can again see the dependencies between all the code in all the packages we've written, we can look at this diagram and see what it can teach us about coupling and cohesion. We still have this very much top-down flow. We have layers and the arrows only really go down. That's a good sign. I'm a little concerned over here, though, where common gilded rose config appears to depend on persistence. I don't feel like this coupling should exist, so let's go and have a look. Here is our config package, and it only has two files in it. One is configuring and one is features. Let's have a look at configuring. And there we see that this configuring depends on this dbconfig. And dbconfig is indeed in common gilded rose persistence, which is in turn in our database module. So now we have this package depending on another submodule, and all really to hold this one function. I don't think that sort of confusion is worthwhile. Let's see where this is used. Well, the answer is only in main. I think we might just move this into the file that needs it. There it is, and it could easily be private. And now if we regenerate our diagram, config has irritatingly moved sides, but it now depends on nothing, and is only depended on by the root and common gilded rose. In fact, we might ask the question, why does it exist at all? Now it only contains this class features, and this features is used, well, it's used in the app and some mains and an acceptance contract. In this case then, I think we might as well move this into the common gilded rose package. So we do that and refactor and regenerate. Now our diagram is simpler again, and we haven't got this sort of ancillary package just hanging off the edge. Well, we have, and it's this common gilded rose HTTP, but that's a thread I don't want to pull today. Now, one side effect of moving features up into our root package, here it is that if we were to add another property, say val is debug, and we'll default that to false. If we were now to pass around our features object, so maybe in our stock list rendering, we want to use that flag, but we do it by passing in the whole of the features, then that now changes our package diagram, so that not only does common gilded rose depend on rendering, but rendering depends on common gilded rose. Now, not all circular dependencies are bad, but they do make things more confusing. So generally in this sort of case, I think I want to pass in just the individual bits of features, whether it's debug or so on, into render, so that render now doesn't depend on the common gilded rose package, or reintroduce the features package that we had before, so that both of these packages could depend on it. At the moment, though, thankfully, we don't have that problem. So we have this nice sweet diagram. As somebody who thinks of himself as someone who thinks in text, I've been surprised at just how useful this diagram has been. Of course, the common gilded rose codebase isn't really big enough for issues of coupling and cohesion to make a great deal of difference, but it's also true that a stitch in time saves 9. If we leave this organisation too long, it can be really hard to impose this structure when we find we need it. Well, I think I'm done for the day. I have just 16 days, 10 hours, 14 minutes and 22 seconds to plug Nat and I's workshop at CraftConf. I guess right here you'll see an interesting discontinuity before I remind you to like, subscribe, and buy the book that I wrote in that price called Java to Kotlin, a Refactoring Guidebook, details of which are in the show notes below. Thanks for watching.